Okay. Okay, so...
Okay, so just to start the day, yeah, Mike.
Okay.
So good morning, everyone. So this day we are going to start with talking about the electricity markets, and we are very lucky to have M.Waterson from Warwick University to talk on that. So before I give the floor to Mike, let me remind you not to use your laptops and tablets during the lectures. Thank you very much, guys. Mike, you're welcome.
Okay, thanks very much. So, you might say, well, what's interesting about electricity? You know, why might one study electricity? And I guess my idea is, well, it's something that everyone takes for granted. Something that you don't really think about. So, you know, you just switch the light on and it comes on, and it's there. But actually, you know, going behind that, there's a huge process, a huge industry working. And actually, it's terribly sensitive, this industry, to various changes. So just to illustrate, I've got some ideas about why one might want to work on electricity, and then I'll have some ideas about why one might not. So what are the advantages of working on electricity markets? Well, one is that if you think about working on industries generally, which is what I normally do, then there are relatively few industries in which you can get good measures of quantity. Electricity is an example of an industry where you certainly can get good measures of quantity, even at relatively disaggregated levels. Data on final prices is normally available, but that's not unusual. Prices are actually the easiest thing in most industries. What's very unusual is to get good data on intermediate prices, prices at the intermediate level. And in most industries, that's pretty much impossible. You know, if you think about another area that I work on is food and supermarkets. In working on supermarkets, you can get final prices, that's easy. You can perhaps get reasonable data on quantities. It's absolutely hopeless trying to get information on intermediate prices. Supermarkets certainly won't tell you. These are commercial secrets. But actually in electricity, mostly, not always, these are quite easily available. And the data is commonly at very high frequencies. In the second lecture, I'll be talking about a case where we've got hourly data. That's a fairly high frequency. And another thing that's good about electricity is that there are many possible exogenous instruments. There are lots of things that, for example, affect demand that are exogenous. One of the things that affects demand is the daylight, which is exogenous. You know, it just happens. Temperature affects demand. We don't control that. So there are lots of exogenous things that happen that, you know, you can, it's pretty straightforward to make a claim that they're exogenous. And so you've got the potential for instruments. What are the disadvantages then? Well, of course there are disadvantages. One is that for people who work on electricity full-time and have worked full-time on it all their lives get very much into the sort of nuances of each country's system, and it's easy to make mistakes if you don't fully understand the market that you're studying. Of course, there is a question about the extent to which electricity runs on a market system or a command and control system, and or a mixture of the two. And in a sense, a mixture of the two is the worst situation from studying them. And they're also, of course, subject to, for perfectly reasonable reasons, government interference, if you like, in the market for various reasons, such as to do with, the government may decide to introduce some form of climate change policy or whatever. Actually, when you get into it, you can't really think of there being an electricity market. There are actually several markets, and I'll explain in just a moment why there are several markets, and it makes it very complex. And the other thing is, and this is sort of disappointing in a way to people who work in the area, but the other thing is that actually it doesn't have a very high profile in economics. And so it's quite difficult to get people outside the area interested in things that you do on electricity, and therefore you need interesting questions that illuminate things, rather than just, anyone can study the demand for electricity in a country, so that's not interesting. You have to have questions which are interesting. And one of the things that can affect questions for the industry, make things interesting, is if there are shocks to the system, and so you can study what happens in reaction to that shock. And the second lecture will be about an example of that. Anyway, so what I want to do, first of all, I'll tell you some facts about electricity, and I'll then talk about the typical structure. I must admit I don't know about the structure of electricity in Russia, but it will have the sort of basic structure that I talk about. Linkages between supply and demand. I'll talk about a typical sort of framework for analyzing an electricity market. I'll talk about market power in electricity, and I'll talk, if I have time, about two examples to illustrate some of these ideas. So that's the plan. So some facts about electricity. Now, if you know about electricity, you will know all these facts. But if you don't know, it's important to understand at least some of these in order to study the subject at all. And the first one, and the most important one, is that at all points in time, demand must equal supply. That's the most important thing in this market. At any, if someone were to switch off the lights here, that would reduce demand. If someone were to switch them back on again, that would increase demand. Somewhere in the system, more electricity or less electricity would have to be produced in response to that. By at all points in time, I mean the system has literally around about 2 seconds of imbalance possible before it starts to collapse. So it's quite an incredible thing, really, that people just do things, I was thinking about when people were watching television yesterday to do with football. When people switch on the TV, there's a sudden increase in demand. Someone somewhere has predicted that and responded to that with producing more electricity. When at half-time, people in Britain, this is a well-known phenomenon, at half-time people go off and do things like making a cup of tea. You can get a sudden huge surge in demand. The people working on the system will know about that. They will know precisely when that happens, and they will react to it. And if they didn't react to it, the whole system would go down. So that's an extremely important thing. But it's also quite convenient, because when you're analyzing the market, you can always assume that supply equals demand. unless the system has collapsed or partially collapsed, where the lights go dim. But of course, as I've just said, demand varies widely during the day, across days of the week, differs between weekend and weekday. It differs across months of the year. And so supply has got to respond to that demand at all points in time. And so, luckily, people are fairly predictable en masse. You know, individually, you're not predictable. Well, some of you may be more predictable than others, I don't know. But individually, you're not predictable. But en masse, you are predictable, luckily. But there has to be a system for responding to that. But the other problem is, and you know, this is so obvious that you probably never thought about it, demand is really relative, particularly in the short run, is extremely unresponsive to price. Nearly everyone doesn't think when they switch on the light or the washing machine or whatever, is this going to cost me something? Perhaps I better not do it. Okay? Good, John? Firms do, of course, if that's...
How much is that due to lack of monitoring? I thought they've done some experiments where if people have, that you can monitor the amounts and the prices are shown, or there's a meter or something that shows in real time what you're using and what it's costing you. People do adjust.
To some extent, yeah. There is actually a novelty effect on that. And so people... A study, this is not something I've studied particularly, but I know other people who studied it, and they say, well, there's a relatively small effect, but there is a big novelty effect on this. So people do it for the first month or two, and then they forget about it. But demand is extremely unresponsive to price. So demand is shifting around a lot, but in order to choke demand off, huge price changes have to take place. Of course, none of us see that, but behind us, huge price changes, and I'll show you that in just a moment. So prices fluctuate enormously at the wholesale level. And traditionally, supply has been very responsive to price signals. How's that? Well, by increasing or decreasing the amount that's generated. So there are some power stations that are designed to operate nearly all the time. There are other power stations that are designed to operate for smaller periods of time, or to operate maybe with a 15-minute lag, or a 5-minute lag, or a 1-minute lag, or a matter of seconds. So there are different power stations which will operate in different ways in order to respond. And so, for example, coal-fired power stations and nuclear-fired power stations, they can't be switched off and on at will. Basically, if you own a nuclear power station, you want to operate it as much as possible, because the marginal cost of producing nuclear power is very low. The fixed cost is very high. A gas-fired power station, the marginal cost of burning gas is very much higher, but the fixed cost is much lower. And so you can afford to operate it intermittently. But there's a problem here, because this is a problem that I think the general public completely fail to understand, unfortunately, which is that we all want more renewable resources to be used in generating electricity, but most, not all, hydro is an exception, but most renewable resources have a very unfortunate feature that they're essentially unbiddable. So coal and gas are biddable. The system, either if it operates according to quantities or according to prices, and you can operate the system either way. Either you can get the engineers to tell power stations what to do, or you can get a series of price signals which will tell where power stations will bid into the system. Either way, they're biddable. You can tell them to do something and they'll, by and large, do it. Wind, you can't tell it what to do. So if it's not windy, you can't produce electricity from windmills. If it's cloudy, you can't produce much electricity from solar power. And so that creates something of a problem for the system. It's a problem that we're only beginning to solve, really. So there's this concern about what happens because the first possibility is that we simply burn more gas when we have more renewables. But anyway, now the final point, this is a technical point, but it's sort of important. It's easy to get, for some people at least, to get confused between, say, megawatts and megawatt hours. So a megawatt is a unit which is normally thought of as a unit of capacity. So a power station may be rated at so many megawatt or gigawatt. Megawatt hours is an amount of electricity produced over a given period of time. So if you think of it in a graph, I've drawn a graph here, there's megawatts in time. If the power station is producing like this, then if you take a segment of an hour, the integral of the curve underneath that's megawatt hours. So we consume electricity in kilowatt hours or megawatt hours or terawatt hours, whatever. But plants are rated in megawatts or gigawatts. Anyway, so the typical framework of electricity markets, what's it look like? It looks like this. Mostly now, I mean, things may change gradually over time, and to some extent they're different in different countries, but for a large part of the industry, there are relatively few inputs into the system, relatively few sources of generation, and the electricity is transported from them through pylons, the wires that you probably noticed, the sort of high wires. I noticed, you probably didn't, but I noticed several on the way from Moscow to here. These high voltage wires, they're usually in sets of 3 or 6. And there's a reason for that, but which I won't go into. But these high voltage wires which carry the electricity from power stations to points of transfer, and that takes place at high voltages, and there's a physics reason for that, which is fairly straightforward. And then when it gets to a point which is much nearer to consumption, it's transferred at some medium voltage. So the high voltage might be 400 kilovolts, for example. The medium might be 100 kilovolts or less, 11,000 maybe. And then it's transformed down again for the last stage of supply at low voltage. But you probably don't see those because nearly always those wires are all underground, and so you don't see the electricity coming into your house. And so we can think conceptually of the industry as being broken up into various segments. There's the generation segment, and then it goes through a transmission and a distribution system, and there has to be some form of coordination, which is commonly, but not always, some form of pool mechanism, where there is some form of control of the system in order to allow this to allow this coordination to take place. So conceptually, all the inputs come into this place, and all the outputs go from this place, and there are many, many outputs, of course, to individual houses and factories and shops and so on. And because of the natural monopoly properties of transmission and distribution, in just about every country, those two things are both regulated. Even if you have a market system, those two things are normally regulated. But generation needn't be regulated because, you know, an individual power station is not, even if it's a very big power station, in a country like Russia, an individual power station would probably only produce 1% of the total power. And so you can have a lot of power stations because transmission is relatively efficient technology. And of course, also at the local level, it doesn't really make sense for there to be two companies with wires down your street underneath the ground. And so that local distribution is normally thought of as a natural monopoly and is normally regulated. But there is a conceptual distinction between distribution and supply. Now, some people find this difficult, so I like to use an analogy when I'm talking about this. You know, if you buy something, might buy something from Amazon, and it comes through the post. Or you could buy something from eBay, and it comes through the post. Or from somewhere else, and it comes through the post. So the distributor is the post service, but the supplier is different. And so you can have competition in supply without competition in distribution. Anyway, so that's the system. And as I say, the market needs coordination. This is normally provided by a system operator. And as I've said, supply and distribution may or may not be interlinked. Now, so talking about generation for a bit, this is Britain. As I say, I don't know what Russia is like on this. This is Britain's system currently. The large blue segment is thermal power, coal and gas. The red segment is nuclear power. The green segment is renewables, and then there's a range of other things. But that's the British system currently, about 2/3 thermal. What about in the future? Well, Britain, like most European countries, is committed to more renewables, and so in the future, in say 10 years' time in Britain, we'll have less thermal, somewhat less nuclear, but a doubling of renewables. And so it will look something more like that, where you maybe have you know, quite a lot more, that it doesn't look like it's double, but actually quite a lot more renewables in the system and correspondingly less thermal. Actually, this is a bit of a trick because that's actually Germany now. But you know, all European countries will be moving in this direction. I don't know whether there are moves in Russia to move in this sort of direction at all. I've no idea. Right, yes, yeah. No, right, okay. Yeah, of course, if you looked at Norway, it would look completely different. It would be all hydro, but Norway, they have a lot of rain. Anyway, so how does the system work? Well, conceptually, it works like this. I've smoothed out the curves, but as I've said, demand moves around a lot over time. It doesn't move much in response to price, but it moves a lot over time. There's much less demand in the night than there is during the day, because factories commonly don't work at night, offices don't work at night. There's more demand in the winter than the summer because some people use electricity for heating, etc., etc. So demand moves around a lot during the day, during the week, during the year. How does the supply respond? Well, there is what's called a merit order, and it works along the lines that I've already indicated. That is, there are some power stations that operate all the time that they can. There are other power stations that are brought, that the next stage up, if you like, the first stage tends to be nuclear, the next stage up tends to be coal, and they will operate most of the time, and then the next stage up will depend on the system somewhat, maybe gas, maybe hydro, and so the system will operate with some power stations operating all the time, others operating less of the time. As demand moves up, you will meet higher and higher points on the supply curve. Why are these points higher? Well, because the marginal costs of the plants higher up the order are higher. The fixed costs may be lower, but the marginal costs, which will determine the sort of cost of producing at that point, are higher. And so there is this merit order. And engineers understood this long before economists understood this, that you have a merit order. And you can either organize the merit order on an engineering principles based on the known properties of the plants, or you can organize it by getting the firms to bid into the system. Currently, most West European countries get companies to bid into the system, either on an hourly or a half-hourly basis. They bid in how much they're willing to supply at a given half-hour or hour period during the day. And then, if you're operating according to a pool system, the operators will decide how much they're expecting to need for that half-hour or hourly period, and that will give you, where that cuts the series of bids, that will give you the price. The system in Britain, by the way, doesn't work quite like this, but that's the basic idea. And so, of course, if something is taken out of the system, suppose you take out something lower down here, then the merit order curve will shift, in that case, to the left, and the prices for any level of demand will be higher. Or if you add something into the system at the bottom, then the prices will be lower for any given hour. And so the system works on this sort of merit order idea with nuclear base load and organization by the system operator. Now, as I say, because...
I have a very simple question, just out of interest. If this merit order dominates the market, can you not use this to manipulate the price?
Yes. And if you think about it, you can. And I'll perhaps come back to this. How does that work? Well, supposing that you own several power stations, and you think, well, if I know about the system enough, I think, well, the price will be at a given point in time, say 100, okay? If I decide that one of my power stations, I'm not going to bid it into the system, the price might go up to 120, okay? And therefore, although I lose money from the one that I decide not to bid in, I gain money from the fact that the price goes higher. Of course, the other firms gain more, but I may still be willing to do that. And so it's perfectly possible in a market system for the generators to distort the system. And people were very concerned about that in the early days, for example, of the British privatization of generation. Yeah. So demand's very inelastic with respect to price, but demand's subject to substantial shocks. And so the price fluctuates greatly. And so what we think of as a completely homogeneous product is not really homogeneous. And so here are some examples to illustrate this. These are actually examples from Germany of the price at a particular point of time in the day, 1430, over the year. And you can see from the graph, if you can see, that sometimes the price is very high, it goes up to 100. Other times, it's near to zero. So huge fluctuations in price over time. Now, we don't see that, of course, but so there is a big risk management problem here for our suppliers. They have to deal with this huge variance in prices. And how they deal with it in a market system is by buying portfolios of electricity. And it becomes quite sophisticated. So, if you're a supplier and you know that prices are going to fluctuate a lot, but you've agreed with your customer, you've agreed with Kern that he'll pay so much per unit, but you know that sometimes you'll have to pay 10 times that much to buy the unit, but other times you'll pay 1/10 of it to buy that unit. What you can do, you can decide to buy some of your units a year ahead, or even 5 years ahead, and maybe buy some of them 3 months ahead, and others of them a week ahead, and others of them a day ahead. Yeah. So there are a whole series of futures markets for electricity. I went, this is a sort of story, but I had one of my ex-students, he became the director of regulation for one of the large 6 companies in Britain, and he invited me, and I went along one day to his company in Scotland, to their headquarters, and it's a bit like, we went into this room where they do this, and it's a bit like going into where you see these pictures of people working in the stock exchange. So on the one side there were the people that were working fairly normally, and they were working on the 5- and 10-year contracts. On the other side there was a couple of guys sat facing these enormous screens, and on the screens there were literally, well over 100 things that they were watching, and they were watching particular points in the network, and they were going to operate short term. They operate some hydro, and they could work out something had happened in the system. They worked this out from the frequency, that something happened in the system, and then they would bid in or decide to come out of the. So it's, as I say, like the stock market, prices fluctuate all the time. People are operating all the time, 24 hours a day, 7 days a week, working on the system to deal with this issue. Renewables, they say, are very variable. Here's an example from Germany again, which is big in renewables. 2 things you can see from this picture. One's easier to see than the other. You can see that the darker picture here is solar, and you can see that solar follows, in aggregate, a fairly standard pattern. It's higher in the summer than it is in the winter. But it fluctuates because sometimes it's cloudy. And that's true even in Britain. Wind, of course, and these lighter ones are wind. Wind fluctuates enormously. It's really variable.
Is the variance also that high for offshore wind?
Yes. Yeah. It's and at the moment, even I was told in Germany, even 4 hours ahead, it's very difficult to predict how much wind there will be. You know, it can suddenly change.
Do you know roughly what the price premium is for reliable supply versus unreliable supply? So if you think about the cost to a buyer of, say, wind, which is high variance. Imagine two sources, one that is high variance like wind, one that's lower variance, like, say, solar, or lower variance even like oil or something. What is the price premium someone would pay to avoid the problems of wind?
Yeah, that's an interesting question. I'm not sure I've got the complete answer to that, but one way of answering that is to say that whereas, say, a conventional coal power station would operate 60% of the time, a wind station would operate maybe 11% of the time.
If there are 5 year and 1 year and 3 months futures contracts, is there sort of derivative trading for wind? Given there's so much volatility, do they try and hedge with sort of? Do people offer contracts 4 hours ahead, saying, my satellite tells me there's going to be wind?
There is derivatives trading. It's relatively less than for commodities. So each bushel of wheat is probably bought and sold 10 times. Okay? It sounds daft, but it is. Each unit of electricity in Britain is probably bought about 5 times. Bought and sold about 5 times. So the market is thinner. And the market is very thin once you get up to a year. But certainly there's trade, whenever these things happen, whenever future markets happen, some clever guy thinks of a way of making money out of combining things in some way, yeah. Anyway, so renewables are very variable. And so, there's a question about how does policy deal with this? One of the ways you can deal with it, actually, and this is very useful from the German point of view, if you think about where Germany is, it's essentially in the center of Europe. I sort of hesitate to say that because there's a certain history behind that remark, but Germany is at the center of Europe, and therefore it's got countries all around it. And so there are interconnectors with each of these countries. And so, given that although correlations are quite high, for example, for wind across countries, they're not perfect. And so it might be windy in Denmark, but not in Germany. And so, transactions take place on interconnectors. Britain, of course, being an island, is much less interconnected than Germany is, but Germany has at least 10 interconnectors with various other countries, from Poland round to Denmark.
So can you clarify that? You mentioned wind in other countries, but I would think what's relevant is interconnection to any part of the electricity grid in other countries,
yes,
right?
Yes,
whether
it's
wind or solar is
relevant. Oh, yeah, no, of course. It doesn't matter what it is, yes. It's just that this reduces the fluctuations, which are created by a variety of things. Wind is one of the most important. Solar is also important in producing fluctuations, but also accidents happen, plants go off stream suddenly, and a big plant going off stream is a big shock to the system. Anyway, so how do economists model this? Well, actually, people model it generally very easy, very straightforwardly. So here's a very simple model. You've got demand, a model of demand, a model of supply, and you set demand equal to supply equal to the volume. And so you can think of this then as being the volume being a function of various things and price being a function of various things. And notice in this, there are some things that are essentially affect demand but have no relation to supply. The level of industrial production, for example, and the temperature have essentially no relation to supply, but they do influence demand strongly. In supply, there will be various things that influence supply that don't influence demand. For example, the prices of the inputs, whether it's windy, whether it's cloudy, and so on. And so you can normally get the system identified fairly straightforwardly because there are enough exogenous variables to identify both sides of the system. Although there is a question that I've put there whether some of the things are exogenous or not. So what sort of issues do people examine? I've realized I've just written that, is there too much power in the generation market? What I mean is there too much market power in the generation market, not too much power, not too much electrical power. How might this manifest itself? Well, one of the ways it manifests itself is the way that I spoke about with Kuhn, through declared unavailability. That was actually a very big problem, or alleged to be a very big problem in the early days of the British system. Why, you know, obviously I'm British, but why do I mention the British system? Well, it was one of the first to move to a market system. And the way that it did this, it was actually quite a bold move, was to separate out all the various segments along the lines of the diagram I put up earlier. And the government decided to introduce some competition in generation, and so they separated out the generation plant, which was all owned by one company, which was a public company, the Central Electricity Generating Board. They separated it out into 3 companies. There was a sort of problem about this. One of these companies was called Nuclear Electric, and really, if you think about it, they play no strategic part in the system. Why? Anyone think why they play no strategic part?
Don't switch it off.
Yeah, you can't switch it on and off. So, and their incentive is always to bid in under a market system. You always bid in with a low. You put such a low price that you're always bid in, because you're going to be paid a much higher price under the pool system. The other 2, the rest of the generation was split actually around about 60-40 to 2 separate companies. But there was something of a problem here that, of course, these people were largely the people that used to work there before, and of course they all knew each other. And they all knew the program that was designed to determine how much electricity would be needed at any time. And they all knew that they all knew that. And so, you know, there was an obvious potential incentive for them to think strategically about how to make money out of the system by gaming it, by strategically declaring plants unavailable. And so how can this be tackled? Well, how it was eventually tackled was by splitting them up further. And of course, gradually, the old program, which probably ran on floppy disks or something, the old program was superseded and new programs came into place. But then there's another problem. Actually, this is a difficult problem because you might say, well, we want to remove all power, all market power in generation. But then, what's the problem then? What's the difficulty then, if you remove all the market power? Anyone think? No?
I would say if everybody only gets its marginal cost, they all make losses because you don't recover the fixed cost.
Yeah, yeah. Or to put it another way, if you remove all the market power, there's never going to be an incentive for anyone to build a new power station. And so, you don't actually want to remove all the market power because then no one builds a new plant. And gradually, new plants will have to be built. It's a problem that we have in Britain, actually. Another problem which arises, and this arises as you change, and this is a problem in Germany, traditionally, the large power stations were sited along major rivers. That was true in Germany, it's true in Britain, or by the sea.
I have a related question to the question you asked. So if by having more renewables, this higher variance, the problem you describe is actually getting worse. Because if you build a new gas station, it's going to run less hours because there's going to be more switching on and off. So how do you solve that then?
Yeah, well, that's right. What the power companies are arguing for is to be paid to idle, if you like. Okay, like a car waiting at traffic lights. You can keep the car running. That involves a real cost, but then if suddenly the traffic light turns to green, or in Russia slightly before it turns to green, you ramp the car up and it starts producing. That's the issue. Yeah. And actually, German power producers have been complaining that they're operating more intermittently, and that's costing them more. And so there are a lot of discussions within Europe about this capacity market idea. But the other issue which arises is that because these power stations were largely along rivers, in Germany, I think largely in the south, along the Ruhr and the Rhine and so on. They're along rivers because you need a lot of water to cool the thing. Or they could be by the sea, because of the need for water. But that means they tend to be sited in particular locations, and the transmission system is all set up for that. And then, if you suddenly have, say, wind off the north coast of Scotland, or off the north coast of Denmark, you have to reinforce the transmission network. And one other issue, which is an interesting issue, which has been debated, is whether it makes sense to have generators and suppliers being part of the same company or not. And there's a big debate about that. What's happening? Oh, sorry. And another issue, which is some people have examined, is whether it's worthwhile having supply competition. I don't know whether you have supply competition in Russia or in wherever you are from. Can you choose who sells you electricity? No? You can't. Okay. Some can. Yeah. Okay. Again, Britain was fairly early into supply competition. We started it in 1999, but it's of moot value because actually, choosing your electricity supplier is not the most interesting thing you can do. I mean, there are other, if you think about what you want to spend your time doing, would you rather spend your time, say, going out to buy a new pair of trousers or yeah, or whatever, I was thinking of buying something, okay? you know, buying a new television is much more exciting than choosing a new electricity supplier. It's, you know, I mean, there are obviously nerdy people around who like doing that, but of which I'm not one, I should say. Anyway, so what I want to do now, I haven't got long left, so I'll just talk about one paper, I think, at the moment. I'll talk about this paper by Catherine Wolfram, which was actually a study. Now, this is actually relatively unusual, if you think about it, but it does have a sort of positive message. There's a positive message and a negative message. The positive message for you, and that is, Americans are very insular people by and large. They're not all insular. I don't think John's particularly insular.
They're not particularly American.
No, well, exactly, yes, yeah. I mean, you're unlike 50% of Americans in that you do have a passport. Americans are fairly insular people, and so you see papers in the top journals about something in downtown Boston, but you know, by and large, you do. But no, I wouldn't point the finger at you. but you don't see papers much about other countries, you know. And even if it's a big other country, like Russia's a pretty big country, you know, to Americans, Russia is a bit like, you know, Belgium, yeah. Yeah. Except it's a bit bigger. You know, it's like on the CIA World Fact Book. Everything is compared to the size of American states. You know. I don't know whether you've ever looked at the CIA World Fact Book, but, you know, it's interesting to read about your country from the American point of view. It's where I read that Britain has cloud cover around 50% of the time. Anyway, so Americans are fairly insular, but here's a paper in what some people would say was the top journal. Other people would disagree, but it's certainly one of the top 5 journals about Britain. So, you know, it is possible to get papers in top journals when you're writing about somewhere outside America, although all the top journals are essentially American. That's the positive message. The sort of negative message is that actually Catherine Wolfram is an American. Who studied at MIT. But
I believe the constraint is not American. It's Cambridge, Massachusetts.
Yeah. but there are other examples. I mean, Americans are actually very interested in, for example, Danish studies on twins, because they can't do it. Okay? Americans are interested in things when there's something that they haven't done that can be studied. And Catherine Wolfram's paper is an example of that, something that they couldn't study, or they couldn't study well enough that she was able to study. And that's why it got into the AER. It was topical, and they couldn't do it. And it was an interesting question. So she's looking at this situation that I was talking about when there were 2 main or 2 strategic firms, and there were various other studies. Hers wasn't by any means the first. Green and Newbery, neither of whom are American, they're both British. Green is very British, much more so than me, really. They have also, and they got a paper in the JPE on this. But her study was quite clever methodologically in studying what happened in the market. The model is quite simple. This is her basic model. So there's a demand side, demand is a function of price and some exogenous variables, as I've said. Marginal cost is a function of quantity and some exogenous variables. And then, essentially marginal revenue is set equal to marginal cost. And there are two alternative expressions of that here. This one, price is equal to marginal cost plus a markup, which is dependent on the elasticity of demand and the way that firms behave. And notice in this one, if theta was 0, then the firms would be setting price equal to marginal cost. If theta was 1, that would actually be the Cournot equilibrium. If theta were above 1, you would be getting between Cournot and collusion. So that's one way of expressing it. Another way of expressing it is that, just rewriting that equation, theta is equal to the price-cost margin times the elasticity of demand. So essentially what she does is looks at this system. And she looks at it two ways. She's got 25,000 observations on price, quantity, etc., etc. Well, actually, she looks at it three ways, but I'm only going to talk about two of them. One is that she does something which is relatively unusual. She essentially does a calibration rather than a regression. So she directly estimates the price-cost margin. How does she do that? By finding out what prices are, by finding out what the marginal fuel is, and then you can work out, roughly speaking, what the marginal costs are. Because, if you think about it, if a gas-fired power station is, say, 40% efficient, then 2.5 kilowatts of gas make 2.5 kilowatt hours of gas make 1 kilowatt hour of electricity, and so you can work out roughly what the marginal cost is. So you can get the short-run marginal cost, and then she uses an estimate that she derives, she gets from the Green and Newbury paper for the elasticity of demand. I mean, you could argue about the value of that, but this is appropriately low, 0.17, and therefore she can calculate theta, because she's got everything she needs to know to calculate theta. The second one I won't talk about. The third one is to estimate a linear demand, it just happens to be linear demand, model of demand and marginal cost. So the first one, as you would expect, the short-run marginal cost is upward sloping, because although any individual plant has a constant marginal cost, added together, given the merit curve, the marginal cost is upward sloping. And so she estimates this across some half-hourly observations, and what she gets is that the price-cost margin is 0.241, and therefore multiplying that by the 0.17, the elasticity of demand, she gets a theta which is really very low, insignificantly different from 0 actually, as it turns out, but the theta is very low, well below 1, almost Bertrand. Now, if she'd just done that, people might say, oh, well, that's because of the way you've done it. And so the alternative method is the more sort of traditional method in a sense, but it's got a nuance, a clever nuance, estimated using two-stage least squares. So quantity demanded is affected by these various exogenous variables, temperature, etc. And then the assumption is in the model, and it turns out to be true, luckily for her, the assumption is that demand elasticity is somewhat different on winter weekdays from what it is on the summer and weekend. That's actually terribly important, because there is a subtlety in identification in this framework. The subtlety is that you can estimate the coefficients for both equations because you've got enough exogenous variables, but it's a well-known problem within these sorts of models. You can't actually estimate theta unless you've got a shift in the slope of the demand curve as well as a movement of the demand curve. And this allows her to have, this fact allows her to have a shift in the slope of the demand curve, which allows her to estimate theta. And so then she also estimates price, function of exogenous variables, quantity, and you see the problem here. The coefficient that you get is theta over 1 plus theta times this other bit, and you've got to try and sort that out. But you can do that using what you've got up here. Yeah, I said that. Oh yeah, this is quite clever. The instrument for price in the demand equation is nuclear availability. So when your nuclear plant goes down, they're all quite big, that's going to affect the price. That's exogenous. You know, they don't go down by, people don't make them go down on purpose. They go down because something happens, the rods get too hot or something, and they have to be switched off for a while. So you get an estimates before, and the results are similar to before. Theta is low. And so her conclusion is that the generators are not making excessive profits. They're a long way from collusion. Now, I don't think I have time to talk about this second paper. Do I? 10 minutes. What do people want to do? Do they want to ask questions, or do they want me to talk about the second model? Going off early for coffee is not an excuse. Okay. Second model. Okay. So I'll have to do this one a bit more quickly. This is one of mine, together with Monica Giulietti and Luigi Grossi. This is in a much lower ranked journal. But actually, we had the easiest ride I've ever had on a journal, so I thought I rather undersold it. But so it relates to a paper by various other people, Bushnell and so on. And what we do, well, their model, which we borrow but add an extra stage to, has a two-stage game. First stage, retailers make retail commitments. Second stage, generators make production commitments. And so, you know, why is the model like this? Well, if you imagine your supplier says, I'll supply you with electricity, and you know, if they do that, then they're going to supply you with electricity for a while. Essentially, they're making a quantity commitment then. Generators make production commitments, but they can make those, a coal-fired power station can make those, they can decide how much to run tomorrow. Okay, so that's a shorter run thing, and so it makes sense to have the game this way, and it makes sense to think of the game as a game in quantities. So it's a two-stage Cournot game you've got here. And of course, everyone knows how to solve a two-stage game, the way that game theorists live their lives, backwards. That's so we solve it backwards. And so we solve the second stage first, given the first stage, and then we solve the first stage. Now, I'm not going to go into the details of this because I don't have time, but the key thing is, what we're thinking about here is two separate market organizations. One market organization is where the generators and suppliers are integrated. The other market organization is where the generators are just generate. And then there will be separate suppliers. And of course, these systems can be mixed. And in Britain, at the time we're talking about, the system was somewhat mixed. There were some people who just generated, merchant generators they're often called, and other people who were integrated. They were both generators and suppliers. Now, if you think about it, both generators and suppliers in the second stage, deciding whether to make production commitments, they're going to maximize profits with respect to quantity. Without going into the details, just thinking about the workings of the model, if you're an integrated firm, if you're a generator, you want to make money on this, so you want marginal revenue you want price above marginal cost. If you're an integrated firm, to the extent to which you're selling electricity retail rather than just selling it wholesale, if you're selling it retail, you want a relatively low price for electricity. In fact, if you were completely integrated, you would want to transfer the electricity at marginal cost. So in that market, if you've got some merchant generators and some integrated firms, in that market, these people have different incentives. The integrated firms want a relatively low price compared with the generators at the wholesale level. So at the retail level, but they didn't look at the retail, but at the retail level, of course, the integrated firms, like the suppliers, want a relatively high price. So they're setting marginal revenue equal marginal cost at the retail level. And so one of the potential problems that exists in a situation with a pool and no integrated firms, a potential problem is double marginalization. Generators make a margin and retailers make a margin. Of course, that depends how much retail power there is. If there's no retail power, there's only one margin. But otherwise, there is a potential problem of double marginalization. If there's no unintegrated firms, the firm makes the margin at the final level. All the integrated firms pass the electricity through at marginal cost and they make the money at the final level. And then you get mixed situations. In the mixed situations, the unintegrated generators and retailers will be in a worse position than integrated firms. I'm forgetting here about risk, by the way. This model puts risk to one side. So what we look at is this situation in Britain, and we look at it between two periods, and these are deliberately chosen. We look at it in a situation after what were called the new electricity trading arrangements were introduced. NETA, it's called. What that was, we moved away from the pool in Britain. We moved away to bilateral bargaining. And so there wasn't a common pool price. And so, whereas before, the generators, whether they were integrated or not, would get paid a common price, we moved away from that. Why? Because the government or the regulator thought that too much money was being made at the generation stage. So we moved away from this, what happened, to this situation of bilateral bargaining, which actually meant that the wholesale prices disappear really from the system. You can't get wholesale prices anymore. But we moved to bilateral bargaining. How do we make sense of this? Well, we got some data from one of the price discovery companies, Platts, on what are called spark spreads. This is the gap between the price that you would have to pay to buy the gas that would make the electricity and the price that you get for the electricity at wholesale level. These are not actually prices, they're assessments. And what do we see? Well, something really straightforward. So we look at the situation before NETA, before this happened, to afterwards, which I've called before better for a reason that I'll explain in just a moment. And you can see that actually the policy worked extremely well from one point of view. Because you'll notice that the spark spread decreased enormously from 0.44 to 0.24. So certainly a lot less money was being made at the generation stage. Wholesale margins fell. Actually, what it led to was extreme difficulties for the merchant generators. It led to particular difficulties for the nuclear power plants, which were used to getting a high price and operating all the time. When they had to bargain, they didn't have all the bargaining power, and so in fact they had to be recapitalized. In other words, they went bust. And you can always make a capital-intensive plant pay if the capital is written down enough. And similarly, Drax was recapitalized, which is the biggest coal plant in Britain. So that part of the policy worked. What about the retail market? Well, so we look at this. Now, there's a lucky thing that in Britain that Scotland is to some extent a separate country. I'm not saying who it's lucky for, but no, it's a separate place in the sense that when NETA was introduced, the new electricity trading arrangements, they were introduced in England and Wales, not in Scotland. And so we're able to compare between the period when NETA was introduced and when the system was introduced into Scotland. We can compare retail, what happened at the retail level compared with wholesale. And so we look at the relative retail margin before and after NETA to before and after BETA. And so here's an example. Just look at the top one here. Whoops. What we find, actually the retail margins, there's a whole lot of detail behind this which I won't go into, the retail margins actually went up in both cases. The blue ones are Scotland, of course, and the red ones are England. They went up in both cases, but they went up more in England and Wales than they did in Scotland. And that difference is clearly statistically significantly different. And so what happened was precisely what the model would predict, but actually the regulator didn't think of, which was margins are reduced at the wholesale level, they're increased at the retail level.
This is really cool. So wait, does that mean that the retail margin was actually 46%? Or is this some...
Yeah, well, yeah, this is there are lots of costs that you can't include, but of course they are costs that are largely fixed. So there's costs of service, cost of distribution, etc., which I haven't put in. But those are all regulated or
And a first order estimate of what the actual margins are?
Yeah.
For you, I mean, what would you say if you were subtract those unobservables?
The distribution is around about 20%, transmissions around about 3%. Then there are various things like what David Cameron reportedly called the green crap, i.e. the climate change levy, which is one of the reasons actually why both of them go up over the period, because so you're probably left with something like 10% maybe, which is partly marketing costs, etc. Which anyway. But the point is that they went up more in England and Wales, which is precisely what the model would predict, than they did in Scotland. In other words, they made more money at the retail level at this stage. This is between 2001 and 2005 I'm talking about. This is when this study when NITA was 2001, better 2005. So what do I conclude from all this? Well, estimating demand and supply of electricity in any country is fairly straightforward. Main thing is to get an interesting question. Are there appropriate natural experiments? In the second lecture, I'll talk about a natural experiment. Interconnection is an interesting issue. Environmental issues are interesting. And demand response, I haven't said anything about demand response yet, but demand response is one of the potential solutions to the problems of variability. That's something that John mentioned briefly, that maybe you can get people to respond more, or more likely, perhaps, you can get firms to respond more.
But Mike, in these models of vertical integration, isn't there a silent trade-off between margins and system stability? Because, because this is not in the model, but if they now, because lower margins invest less, there will be less marginal stations to switch on. So at some point it will crash where it wouldn't have crashed otherwise. Yeah,
well, in my view, my personal view, NITA was a mistake.
Because of that reason?
Yeah.
Is anyone modeling this? That's like the general versus particular thing,
yeah,
right?
So I would say that there is a sort of gradual realization of this, and of course responses like capacity payments.
Is that happening, capacity payments?
Well, it's being discussed, and it will come in, I think, next year probably.
Thank you.
Those things are the responses that are taking place.
So Mike, when you mentioned this issue about the low responsiveness in the very short run to prices, but of course we know they respond in the somewhat longer run. So one of the things I've been surprised by, I talked to somebody before working in electricity, why they don't have more marketing behavioral types run experiments on what kinds of price adjustments make a difference. So for instance, I'll just make it simple. They may not, in the very short run, they may not adjust to say prices if they want to watch the game or etc. But if you get them to get used to an adjustment between say just night and day, they might make, if you raise the average price enough, they'll make adjustment. Or I was wondering even if you hired a marketing firm, whether they would do something like the following. Let's say you want to nudge people who are just on the verge of making a difference between their morning and evening usage, and you want them to use more in the evening. So you tell them, you send them a note sort of saying, you are within blah, blah, blah of getting it down there. And if you do, you get a bonus. So they do it in terms of you get, it becomes like rewards. You make it like lotteries and things of that sort. So instead of just having a fixed price or a set, but do it in ways that are behaviorally motivating. I mean, have people been doing experiments like that?
Yes. Yes, there's a guy in Chicago called Rob Metcalf who does exactly that thing, and the thing that works the best is when you say that your neighbors do something that saves them electricity. So there's kind of a lot of this peer effect stuff, which is really amazing, that, you know, when you learn that your neighbors have adopted a particular energy efficiency thing, you end up adopting yourself, and that's one of the things that actually lasts longer than those kind of novelty things, you know, when you just get a little monitor.
The other answer is that obviously people do this sort of thing for the companies, but they're not necessarily sensible. And here's a disappointing story. A PhD student of mine, I arranged with a company, they'd done a lot of experiments on smart meters. Smart meters are the things in your house which tell you how much you're using. And it was, in some senses, very sophisticated what they did. They had several different versions of the meter. They had several different incentive systems. And it turned out to be a complete disappointment. The reason is that they asked people whether they wanted to participate or not, and they kept no records of the people who said they wouldn't. So it completely mucked it up. You know, she spent a long time on this to no good effect, I'm afraid, because you know you obviously need an untreated set of people, and they just didn't think to keep that set of people. which is really disappointing.
Yeah, we have a last question, I guess.
Yes, maybe my question is not so much related to your last paper, but about the experiments and maybe the demand response. Do you know about this? Again, the experiment that was conducted by the Russian government when they refused to switch to the summertime, to winter time again. Do you know if there are some studies on that?
I don't know of any studies on that, but that would be interesting. Yes, if you get, or particularly if you get a switch in some parts and not in others, or something like that, then that would be an interesting thing to look at. Yeah, because it does have effects on how much people use, obviously. Yeah, yeah, that's.
Okay, thank you, Mike.